In this video, we are going back to limits to learn about a special rule called L'Hopital's rule. L'Hopital's rule allows us to find the limit of various functions that we might have struggled with a little bit before, but we couldn't have learned it earlier when we were doing all of our limits before because we didn't know what a derivative was yet. In order to do L'Hopital's rule, you have to know how to do a derivative. So now we're ready. Here's the rule. It says, suppose that f and g are differentiable functions and that g prime of x is not equal to 0 near a, except possibly at a. Then suppose that the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x is equal to 0, or suppose that the limit as x approaches a of f of x is plus or minus infinity, and the limit as x approaches a of g of x is also plus or minus infinity. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So what this is saying is if you're taking a quotient of functions and you're looking at the limit and you end up with 0 over 0 or some form of infinity over some form of infinity, and the functions happen to be differentiable, you can take the derivative of the top and the derivative of the bottom and take the limit of that result instead, and it's going to be equal to the original limit, provided that the limit exists. So let's do some examples where we do this. Now, my main warning for you about L'Hopital's rule is students seem to really enjoy using L'Hopital's rule, but you can't use it all the time. It has to be in one of these situations. You need to have your limit in the correct form, 0 over 0, infinity over infinity, negative infinity over negative infinity, some form of infinity over some form of infinity. And your functions need to be differentiable, and the derivative of the denominator needs to not be 0 near the value that you're approaching. If you don't have those conditions, then you can't use this rule. So it's important to always check the conditions before you just start taking derivatives everywhere. Let's do an example. Let's find the limit as x approaches 1 of natural log of x over x minus 1. So first, let's think what would happen if I tried to plug the 1 in. If I tried plugging 1 directly in, we're going to get 0 over 0, because natural log of 1 is 0, and then 1 minus 1 is 0. So 0 over 0 is an appropriate form to use L'Hopital's rule, so that's good to go. But we need to make sure our functions are differentiable. Can we take a derivative of natural log of x? Yes. Can we take a derivative of x minus 1? Also yes. Is the derivative of x minus 1 non-zero? Well, if I take the derivative of x minus 1, I get 1. That's non-zero, so we're good to go. We can use L'Hopital's rule to do this. Now, notice that when we had 0 over 0 before, that was our cue to do algebra. But on this particular problem, we would be kind of stuck. We wouldn't really know what algebra to do to try to simplify this. So that's why this rule comes in handy. So the limit as x goes to 1 of natural log of x over x minus 1 Using L'Hopital's rule, which I like to indicate that's what I'm doing by doing an LH over my equal sign. Just a note to myself that I'm using L'Hopital. This is equal to the limit as x goes to 1 of the derivative of the top over the derivative of the bottom. Now, a very common mistake when using L'Hopital's rule is that students want to do a derivative of this whole thing using a quotient rule. And that's not how this works. It's just the derivative of the top over the derivative of the bottom. So the derivative of natural log of x is 1 over x. The derivative of x minus 1 is 1. So when I simplify, I have a limit as x approaches 1 of 1 over x. Now when I directly plug that 1 in, I get 1. And that is the answer to the original problem. So that's how L'Hopital's rule works. You have to make sure your functions are differentiable. You have to make sure the derivative of the denominator is not 0. And you have to make sure that you're in a 0 over 0 or some infinity over some infinity situation. And then you can just take derivatives of the top and bottom and do the limit that way. Let's do another example. How about the limit as x approaches infinity of e to the x over x squared? Okay, well, if I think about plugging infinity in, e to the infinity would be infinite, and infinity squared is infinite. So I'm in an infinity over infinity situation, so L'Hopital's rule could apply. Are my two functions differentiable? Yes, they are. I can take their derivatives. Is the derivative of the denominator non-zero, at least when we're getting close to infinity? Well, the derivative of the denominator is 2x, and that's non-zero as long as x isn't 0. So we're good. So we can do this using L'Hopital's rule. I can take the derivative of the top and the derivative of the bottom. The derivative of e to the x is itself, and the derivative of x squared is 2x. And now what happens when I try to plug in infinity? Well, I would be in infinity over infinity. So what went wrong? Nothing went wrong. We just have to do it again. Sometimes you just have to use it more than one time, and that's okay. So before we can use it again, make sure that our functions are still both differentiable. They are. And that the derivative of the denominator is non-zero, at least when you get close to where we're taking our limit. The derivative of the denominator is 2, so we're okay. So using L'Hopital's rule again, we get the limit as x approaches infinity. Derivative of the top is e to the x, and derivative of the bottom is 2. And now when I try to take my limit, I get infinity over 2, which is still infinite. So there's the answer to the original problem. Let's try another one. The limit as x approaches infinity of natural log of x over the cube root of x. And the first thing I'm going to do, since I know I'm probably going to need L'Hopital's rule, I'm going to rewrite that denominator as x to the 1/3 power, just to make my derivative easier. So think about what happens if we were to plug in infinity. A natural log of infinity would be infinite, and a cube root of infinity is still infinite. So this is infinity over infinity. Are my two functions differentiable? Yes, they are. Is the derivative of the denominator non-zero, at least close to where I'm taking my limit? Correct. Because if I take the derivative of the denominator, I get 1/3 x to the negative 2/3. That's non-zero. We could potentially be dividing by 0, but we're okay because we're not plugging in x equals 0. So let's see what we get when we do L'Hopital's rule on this guy. A limit as x approaches infinity of natural log of x over x to the 1/3. Using my L'Hopital's rule, I get a limit as x approaches infinity. The derivative of natural log of x is 1 over x, and the derivative of x to the 1/3 is 1/3 x to the negative 2/3. Now let's simplify this. Dividing by the 1/3 is the same thing as having it multiplied by 3, so I can put the 3 in the top. And then this guy's an x to the negative 1, and this is x to the negative 2/3. When I simplify, I get an x to the 1/3 in the denominator. Now when I take this limit, I have 3 divided by a really huge positive number, and that goes to 0. All right, so all that we've worked with so far are limits that are of the form 0 over 0 or infinity over infinity, and those are what L'Hopital's rule are for. Those are called indeterminate forms. But we do have other types of indeterminate forms as well. L'Hopital's rule can be used for other types, but you have to do some algebra first to put it in the proper form to use the rule. So we're going to talk about the indeterminate form of 0 times plus or minus infinity. So if the limit is of the form 0 times some form of infinity, we need to rewrite the problem so it is of the form 0 over 0 or a plus or minus infinity over plus or minus infinity. So you'll have to rewrite it so it's in the proper format before you can apply L'Hopital's rule. But that's not too bad to do. So an example where we're going to have to do this, we'll just start the example here. Let's look at the limit as x approaches 0 from the right side of x times natural log of x. So if we think about plugging in a 0 and slightly on the right side of 0, this x is going to 0, and my natural log of x is going to negative infinity. So I have a 0 times negative infinity situation. So I want to rewrite this as a quotient. There's 2 ways to do that. I can either write this whole thing as natural log of x divided by 1 over x, or I can write it as x divided by 1 over natural log of x. And the first option is easier for us because of how we're going to have to take derivatives. So we are going to rewrite this so that it looks like natural log of x over a 1 over x. This is still the same problem. But now if I plug in my 0, I get a negative infinity on top, and I would get a positive infinity on the bottom. And that's an appropriate form to use L'Hopital's rule. So we just have to check, can I take a derivative of both of those guys? Yes, I can. And is the derivative of the denominator non-zero, at least near 0? Yeah. So let's do this with L'Hopital's rule. But I'm going to rewrite that denominator first to make our derivative easier. So using L'Hopital's rule, I get a limit as x approaches 0 from the right. Derivative of the top is 1 over x, and the derivative of the bottom is negative x to the negative 2. So now let's simplify this. I know it's negative. I have a limit as x goes to 0 from the right of negative Well, this is x to the negative 1, and this is an x to the negative 2, and when I simplify, I'm going to get just an x, because it's a negative 1 minus a negative 2 power, which is a positive 1 power. Now when I take this, as x approaches 0 from the right, I get 0. So if you have a situation that's a 0 times an infinity, you just have to rewrite the problem so that you're dividing by 1 over one of your two functions. And then you'll be in the proper situation to use L'Hopital's rule. Now, what if we have a different type of indeterminate form? What if we have something that looks like infinity minus infinity? We'll need to somehow rewrite it as a quotient. Because L'Hopital's rule involves quotients. Now this one sounds like it might be a little difficult, but usually it's not too bad. Usually involves just a little bit of rewriting using algebra. So an example of this type, let's find the limit as x approaches pi over 2 from the left side of secant x minus tangent x. Now this, if I try to plug in pi over 2, my secant x goes to infinity and my tangent x goes to infinity. So I'm at an infinity minus infinity situation, and we have no idea what infinity minus infinity is. So we need to try to rewrite this somehow as a quotient. I would suggest with trig functions like this, that you convert it to all sines and cosines before you do anything else. Secant is 1 over cosine. Tangent is sine over cosine. And now look at that, I have a common denominator, I can write it together as one fraction, and then we'll have a quotient like we need. So when I combine this together as one fraction, we have a limit as x approaches pi over 2 from the left of 1 minus sine of x over cosine of x. And now if I think about plugging in pi over 2, sine of pi over 2 is 1, so my top is 1 minus 1, which is 0. And cosine of pi over 2 is 0. So I'm in a 0 over 0 situation. I can take the derivative of both the top and the bottom, and the derivative of cosine is not exactly equal to 0. It can be all sorts of different values. So we're okay to use our L'Hopital's rule. Using L'Hopital's rule on this, I have to do the derivative of the top and the derivative of the bottom. For the derivative of the top, derivative of 1 is 0. Derivative of a minus sign is a minus cosine. And the derivative of cosine is negative sine. So now when I look at this, and I plug in my values, I would have a cosine of pi over 2, which is 0, and a sine of pi over 2, which is 1, but it's negative. Regardless, I get 0, because I have a 0 over a 1. All right, so now we've talked about indeterminate forms of the form 0 over 0, plus or minus infinity over plus or minus infinity. We've had 0 times a plus or minus infinity, and we've had infinity minus infinity. And there is one more type that we have to learn how to deal with, and it is the most difficult one out of all of these possibilities for L'Hopital's rule. So our last type of indeterminate form is if you get something that looks like 0 to the 0 power infinity to the 0 power or 1 to the infinity power. We will have to take a natural logarithm in order to do these problems. An example of this. Let's look at the limit as x approaches 0 from the right of 1 plus sine of 4x to the cotangent of x power. So let's take a look at what happens if we plug in 0. Well, sine of 0 is 0, so I would have a 1 inside the parentheses. And the cotangent of 0, that goes to infinity. So I'm in a 0 or a 1 to the infinity situation. This means we need to use a logarithm. How we do that? Well, we're going to create a new variable. I'm going to call it y. Let y equal 1 plus sine of 4x to the cotangent of x power. Then the natural log of y is equal to the natural log of 1 plus sine of 4x to the cotangent x power. But now, because I have natural logs, that cotangent x power can come down in front of the logarithm. And so we get that the natural log of y is equal to cotangent of x times the natural log of 1 plus sine of 4x. And now let's consider the limit as x approaches 0 from the right of natural log of y, which is the limit as x approaches 0 from the right of cotangent of x times natural log of 1 plus sine of 4x. Now what happens when I try to take this limit? Well, my natural log is becoming a natural log of 1, which is 0. My cotangent is going towards cotangent of 0, which goes towards infinity. So this is now infinity times 0, which we still can't use L'Hopital's rule on that, but we know how to deal with this situation. I have to rewrite this as a quotient. So instead of multiplying by a cotangent, I'm going to write it as dividing by tangent. So I can rewrite my problem as the natural log of 1 plus sine of 4x divided by tangent of x inside of my limit. Now when I try to take the limit, I still have a 0 for the top, and then tangent of 0 is also going to be 0. So I'm in 0 over 0, so we're good to use L'Hopital's rule. Can I take the derivative of these functions? Yes, I can. And the derivative of tangent is non-zero, so I'm good to use my L'Hopital's rule. Now, to take these derivatives, you're going to need a chain rule for the derivative of the top. So using my L'Hopital, the derivative of the top is 1 over the stuff in the parentheses times the derivative of the stuff in the parentheses. Well, the derivative of the stuff in the parentheses is another chain rule. Derivative of sine is cosine, and the derivative of the very inside function is 4. That was a double chain rule on the top. On the bottom, derivative of tangent is secant squared. And now let's see what happens if we try to plug in 0. Well, I know that sine of 0 is 0. So this whole first fraction here, this is 1 when I take the limit. Now cosine of 0 is 1. So this whole piece here is 1 times 4, which is 4. And then I have secant squared of 0. Well, secant is 1 over cosine. So this guy is going to 1 over cosine of 0, and the whole thing squared. Cosine of 0 is 1. 1 over 1 squared is still 1. So when I take the limit, all that I have is 4. This limit is equal to 4. Now, hold on there, because at the end of all these other problems, I just put a box around the answer and I was finished. We're not finished here. Because remember, we are the ones who introduced that natural log to the problem. That's not the original problem. So we found that the limit as x goes to 0 from the right of the natural log of y is equal to 4. But we want just the limit as x goes to 0 of y, not natural log of y. Well, how do I undo a natural log? We use an exponential. So to undo the natural log, I get to raise both sides. We have e to both sides. So I'm going to get that the limit as x goes to 0 from the right of y is equal to e to the 4th power to undo that natural log. And that is the answer to the original limit before we introduce the natural log. So when you're in one of those situations where we have a 1 to the infinity, a 0 to the 0, or which one did I say? Or infinity to the 0, and you don't know what to do, you take a natural log of both sides, do the limit of the natural log, and then rewrite your answer as e to your answer to get the original answer to the original problem. All right, so that's about it for L'Hopital's rule. L'Hopital's rule tends to be a favorite of students because I like taking the derivatives of the top and the bottom. It makes a lot of our limit calculations much easier. But it is very important to make sure that you can actually use L'Hopital's rule before you start just applying it to everything. So you should always check the conditions, make sure you're in 0 over 0, plus or minus infinity over plus or minus infinity, and that your functions are differentiable and the derivative of the denominator is not 0. If you meet all the conditions, then go ahead and use L'Hopital's rule wherever you want. If you have any questions, feel free to drop them below. If you're a current student, you can also ask through email or office hours, and I will see you in the next video.